Okay, so what we're going to be looking at now is we're going to be looking at first order linear systems and systems of differential equations, and we're going to start with these first order linear systems. So if you look, what you've got here is you've got a system of differential equations of this form, and you're going to notice that the value that we have on the left hand side is the value of the derivative. Call it x1 prime, x2 prime, all the way down to xn prime. And then what we'll have is we'll have a11t, okay, and then times x1 of t, a12 of t, times x2 of t, and then so on and so on until we get a1 of t, xn of t, plus b1 of t, okay? Now, you may actually want to pause for just a second if you want to write all of this down, because then I'm going to actually kind of show you some features of this system that are going to become really, really important as we continue on through this chapter and through this discussion of linear systems. Okay, so now each one of these what we call the AII, A11, A21, all the way down to AN1, they're all functions, okay? They're going to be functions of t. And because they're linear, they're all going to be functions of t and t only, all right? And then what that kind of means is that our dependent variable is going to be these x1 of t's. These are like, that becomes like, it's kind of like the substitute for y's, right? Like what we had before were y's, and we had y primes and y double primes. Now we've got these different functions of x, okay? And so we're also going to distinguish here now, too, between what we call a homogeneous system and a non-homogeneous system. And so it's slightly different, although it's very much related. A homogeneous system is going to be if these b1 of t's, b2 of t's, etc., 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 down to bn of t, are all equal to 0. And if they're not all equal to 0, then what we have is called a non-homogeneous system. And so that's really related to everything that we've been talking about before with regard to homogeneous and non-homogeneous systems. So if what I do now is I'm now going to construct basically a matrix, all right? And I want to just do this right now just to show how this kind of definition actually works within what we've learned previously with regard to linear algebra. So I'm going to scroll down here for just a second, and what I'm going to get is on the left-hand side, I'm going to have a vector made up of derivatives. Okay, so I'll have the vector made up of derivatives, and so that'll look like this. x1 prime, x2 prime, all the way down to xn prime. And so that's my vector of derivatives, and that'll equal then, and what we're going to see is to notice that x1 of t all the way down, x1 of t, x1 of t, x1 of t is going to correspond to this first column, right? And you can see that we've got the same notation that we've been using for matrices here too. All right, so we've got the matrices notation in addition to the notation for the function. So that's going to equal a matrix function. A matrix function made up of a11t, a12t, so on and so on and so forth, all the way down to a1nt. And then we're going to have all the way down, we're going to have those functions that we had inside of the system down to n1t, n2t, so on and so on and so forth until we get to annt. And then our solution vector here is going to be x1, x2, x3, all the way down to xn. And so we will be solving for x, this vector right here, which is actually going to be called the vector x. Okay, so that's the vector x there. And so that's going to allow us some shorthand. And we'll get into that shorthand a little bit more inside of the next section. Okay, but when we're generating these systems, you want to be thinking to yourself, okay, well, I can actually translate my systems into these matrix equations. All right, and we'll get some more notation on that in just a little bit. Now this vector x, okay, x1 through xn, which are functions, is the solution to the system. All right. So if we have an n by n system, we're going to have n different solutions to the system. Okay. Or we're going to have one solution, but it's going to be made up of n different functions. I should actually restate that. One solution, n different functions. Okay. And so what it's going to be is, you notice it's an n-tuple, right? But it's an n-tuple of functions. One for each one of our differential equations. So now let's take a look at a system of differential equations, and what I'm going to do is I'm going to use kind of a very basic method for going about solving one of these systems of differential equations, and then we're going to use this in order to actually kind of like illustrate all the different things that you can do with the systems. Okay? All right. Now, in addition to that, we're also going to be talking about the vocabulary, so we'll kind of like look at what solutions look like, we'll look at the vocabulary, and we'll also look at like a solution method. So don't get too caught up on the solution method either, by the way, because we're going to be learning other ones that might be a bit more efficient. You do want to at least understand the one that we're going to be doing right now, and because it happens to be very effective for when we're working with systems that have constant coefficients. Okay? So let's consider this system, x1 prime equal to x1 plus 2x2. We'll have an x2 prime, which will equal 2x1 minus 2x2. And so that'll then give me x1 prime, x2 prime, is going to equal then, and our matrix is going to have 1, it's going to be 1, 2, 2, negative 2 times x1, x2. So if I were going to transform it into a matrix, that's what that would look like. Okay? But we're not going to use that quite right now. I just wanted to kind of just generate one, see what it looks like. Okay? Now, what we're going to do in order to solve this is we're actually going to rewrite this as in operator form. Okay, and so that'll look like this. It's going to be x1 prime minus x1, okay, minus, and then in this case, 2x2 is going to equal 0. And then, so we'll set it equal to 0, and then we'll have x2 prime minus, or plus 2x2, okay, minus 2x1 is going to equal 0. And I'll go in and I'm just going to rearrange this so that my x1s are all in the same place. So this will get rewritten as x1 prime minus x1 minus 2x2 is equal to 0. And then x2 prime plus, negative 2x1 plus 2x2 plus x2 prime plus 2x2 is going to equal 0. Now what I'm going to do is I'm going to take this and I'm going to rewrite it as operators. So I'm going to get now d minus 1 x1 minus 2x2 is going to equal 0. And then negative 2x1 plus d plus 2 x2 is going to equal 0. Now what I'm going to do is I'm basically going to do some work where we're going to do some elimination, but we're going to use differential operators, which is a little weird when you think about it, but from a computational standpoint, it's going to seem kind of familiar. So what we're going to do now, it's going to be a little strange, but it's actually going to work out really well for us, is we're going to kind of think about this as a system of equations, but we're going to be working with operators. So we're going to first, right, operate on the top matrix, the top system by d plus 2. So we're going to operate by d plus 2, and that's because what we want to do is we want to get the x2s to be the same. We're eventually going to want to be able to like eliminate the x plus 2s. So what do we have to do? We have to get them to be the same. And so the bottom one, we're then going to also multiply by positive 2. Okay? So that way on the top, we'll have negative 2 times d plus 2 x2. And on the bottom, we'll have positive 2 times d plus 2 x2. Or operated d plus 2 x2. So now we'll do that. So that's going to give me d plus 2 times d minus 1. Not really times. D plus 2 d minus 1 x1 minus 2 d plus 2 x2 equals 0. And the bottom is now going to be negative 4 x1 plus 2 d plus 2 x2 equals 0. When we combine them, what we'll now get is we're going to get d plus 2 d minus 1 x1 minus 4 x1 equals 0. Now what we have is we basically have a second order differential equation that we can go in and then solve. So let's actually simplify. We're going to get d squared plus 2d minus 2 x minus 4x1. And so that's going to be then d squared x1, or yep, d squared x1 plus 2d, or excuse me, plus d x1 minus 6x1 is going to equal 0. And if we rewrite that, that's now going to give me d plus 3, d minus 2, x1 equals 0. And what I'm left with then is that x1 of t is going to equal c1e to the negative 3t plus c2e to the 2t. And that's my x1. Now what I'm going to do is I'm going to take x1 of t and I'm going to plug it back into this first differential equation. Okay? Because this first differential equation, we don't have to take derivatives of x2. It's actually going to be fairly straightforward for us. Okay? So we're going to get d minus 1, and that'll operate on c1e to the negative 3t plus c2e to the 2t minus 2x2 is going to equal 0. Okay? So we'll take the derivative. What this is saying is we'll take the derivative of c1e to the negative 3 plus c2e to the 2t. So that's going to end up being negative 3 c1e to the negative 3t plus 2 c2e to the 2t minus c1e to the negative 3t minus c2e to the 2t minus 2x2, 2x2, not x squared, x2 equal to 0. Now what I can do is I can just go in and I can just basically rearrange to give me everything that I want. So this is going to end up being, right, we'll combine like terms. So it's going to be a negative 4 c1e to the negative 3t, right, plus c2 e to the 2t, right, minus 2x2 equal to 0. So we'll get now that negative 2x2 will equal 4 c1e to the negative 3t plus c2e to the 2t. Okay, so x2 is then going to equal negative 2 c1e to the negative 3t minus 1/2 c2e to the 2t. So the solution to our differential equation then is going to end up being x1 equals c1e to the negative 3t plus c2e to the 2t, and then x2 will equal negative 2 c1e to the negative 3t minus 1/2 c2e to the 2t. Actually, this should be a plus. This should be a plus, right? Because this side should actually be a minus, right? Because we should have subtracted over. Okay? And this is going to be where C1 and C2 are arbitrary constants. So now, let's say, for example, that I want to figure out what C1 and C2 actually are, right? So I have this idea. We have an initial value problem, okay? And because these are first order linear, okay, that is that I only have a single derivative, all right, I will need one initial value for each of my solution equations, okay, for x1 and x2 in this case. In this case, so like let's say for example that what I say is I'm going to say that x1 of 0 is going to equal 0, or yeah, you know what, x1 of 0 will equal 1, and we'll let x2 of 0 equal 1. Okay, since this is first order, it's actually fairly simple. What we can do here is we're going to say, okay, well then 1 is going to equal c1e to the negative 3 times 0 plus c2e to the 2 times 0. Okay, and then 1 is going to equal c1e is going to be equal to negative 2 c1e to the negative 3 times 0 plus 1/2 c2e to the 2 times 0. Okay, so that means that we're going to get 1 is going to equal C1 plus C2. And then we're also going to have 1 is going to equal negative 2C1 plus 1/2 C2. We can then just set up a augmented matrix here. If we just kind of turn it around, we'll end up with 1, 1, 1, and negative 2, 1/2, 1. And when we take the RREF of that, that's going to end up giving me now 1, 0, negative 0.2, and 0, 1, 1.2. So the results of the initial value problem are going to be that x1 of t, my function, is going to then equal negative 0.2 e to the negative 3t plus 1.2 e to the 2t. And then x2 of t is going to equal, well, we'll take negative 2 times negative 0.2. Okay, so that's going to give me negative, it's going to be positive 0.4 e to the negative 3t plus, and then this will be 1/2 of 1.2, and so that will end up being 0.6 e to the 2t. And so this is a particular solution to the system, or a solution to the initial value problem. And so that's actually how we're going to go about finding C1 and C2. You're actually going to have to use some system of equations. For my class, totally fine for you to go use some, obviously to use some technology in order to go about doing that. Okay? Let's take a look at another example. So let's take a look at this initial value problem. So x1 prime is going to equal 2x1 plus 5x2. x2 prime will equal negative x1 minus 2x2. And so we'll have x1 of 0 is going to equal 0 and x2 of 0 is going to equal 0. So just like in the last example, what we're going to do is we're going to rewrite this in operator form. So this is going to be x1 prime minus 2x1 minus 5x2 is going to equal 0. And then I'm going to have x1 plus x2 prime plus 2x2 is going to equal 0. Okay? Rewriting that as operators, that's going to give me d minus 2 x1 minus 5x2 is going to equal 0. And then just x1 plus d plus 2 x2 will equal 0. Now, on the top, I'm going to operate by d plus 2. And on the bottom, I'm going to multiply it by positive 5. Okay, so we'll multiply the bottom by positive 5. So that's going to give me d plus 2 times d minus 2 minus 5x2 equals 0. Or minus 5 times d plus 2, or 5, yeah, d plus 2 x2 equal to 0. And then we'll have d minus 2, or excuse me, and then we'll have 5x1 plus 5 times d plus 2 x2 equal to 0. And then we're just going to combine our like terms. We're going to add the two equations together. We'll get d plus 2 times d minus 2. This should be an x1. Plus 5x1. And these will cancel. And we'll end up that equals 0. Now, simplifying, I get d squared, okay, minus 4d, excuse me, minus 4x1 plus 5x1 is going to equal 0. So that means that d squared, and this will be minus 4x1 plus 5x1, d squared plus 1x1 is then going to equal 0. Solving this second order differential equation is going to give us that r here is going to equal plus or minus I. Okay, so my solutions are going to end up being that x1 is going to equal c1 cosine x plus c2 sine x, or t, whichever one we want to choose. How about we'll use t. c1 cosine t plus c2 sine t. Okay, utilizing the result of our auxiliary polynomial r equals plus or minus I. So that's x1. So now what I'm going to do is I'm going to go back up and I'm going to utilize this first equation up here in order to solve for x2. Okay, so I'm going to rewrite that. I'm actually going to rewrite it as d minus 2, right? And then this will be c1 cosine t plus c2 sine t minus 5x2 is going to equal 0. And just to make my life a little simpler, I'm going to move that 5x2 over to the other side. And that's then going to then be equal to d minus 2 c1 cosine t plus c2 sine t. Okay? So now we'll take the derivatives. So the derivative of c1 cosine t plus c2 sine t is going to end up being negative c1 sine t plus c2 cosine t. And then will be minus 2c1 cosine t minus 2c2 sine t. And that'll equal now 5x2. We can combine our c1s and our c2s. So this will give me now then negative, or rather negative c1 sine t minus 2c1 cosine t plus c2 cosine t minus 2c2 sine t is equal to 5. And if I just factor out, I get c1 times negative sine t minus 2 cosine t plus c2 times cosine t minus 2 sine t. And that'll then equal 5x2. Then I'm going to divide by 5. And so what I'm left with is, this whole thing divided by 5. And unlike in other cases, we want to make sure that our C1s and our C2s, that we actually keep in that division by 5. It's actually going to end up being really, really important. So we divide through by 5. So we're going to get C1 over 5 times negative sine t minus 2 cosine t plus C2 times C2 over 5 cosine t minus 2 sine t. And that'll equal x2. So that's x2. All right. And so given that we have an initial value problem here, that's going to kind of help us out, right? We've got now x1 of 0 is 0 and x2 of 0 is equal to 1. Okay, x1 of 0 equals 0 and x2 of 0 equals 1. So I'm just going to plug in my values. All right, we're going to start out up here at x1. So we're going to get 0 is going to equal c1 cosine of 0 plus c2 sine of 0. Okay, so sine of 0, that's going to end up being 0. So that means that c1 actually ends up equaling 0 because c2 times sine 0 is 0. So c2 will just end up being 0. And then now we can substitute that back in to get x2. So we're going to get x2 is 1, right? And c1 is 0. So the first term, this first term all goes away. That's going to be 0 plus, all right, so we're going to have c2 over 5 times cosine of 0 minus 2 sine of 0, okay, will equal 1. So that gives me now that c2 over 5 times 1, okay, because this is just going to be zeroed out, is going to equal 1. And so consequently, that's going to give me that c2 is going to equal 5. And there we go. So that's going to allow me to get x1 and x2. So I go back up to x1 just to see what it is. x1 is c1 cosine t plus c2 sine t. Well, c1 0. So x1 is just going to end up being equal to 5 sine t. And x2 will then be equal to, and it'll just be the second part because c1 again is equal to 0, is going to equal 5 over 5, so that's 1. So it's just going to end up being 1 times cosine t minus 2 sine t. Okay, and that's this equation right there. And so that just equals cosine t minus 2 sine t. So my solution to my system, my particular solution, is this one. x1 equals 5 sine t, and x2 equals cosine t minus 2 sine t. All right. So that helps to kind of introduce us to these systems of first order differential equations, right? They're all linear. These all have constant coefficients. And so it's pretty straightforward how we can go about, solving them. Now, you might imagine that as we get more and more and more of these systems, and as they get as they end up being like non-homogeneous, for example, these were all homogeneous. It gets more and more complicated. And so the chief ideas that we're going to be working with inside of this particular chapter are going to be, well, how do I solve those new systems of differential equations? Okay? So this completes this particular lesson.